Hello, welcome to this module in this massive open online course. Alright, so this module, alright, so what we are going to look at is basically in this course is signals and systems, the properties of signals and systems. Alright, so this course concerns itself with, as the title implies, we would like to look at signals and systems, two of the fundamental quantities which are relevant in all of electrical, electronics and communication engineering, and relevant at a very profound, relevant at a in a very profound sense, since they are fundamental, have a fundamental relevance or understanding, or their knowledge is fundamental to understanding the various concepts or the various aspects of different applications in electrical, electronics and communication engineering. Correct. So, what we are interested in this massive open online course is to understand, as I have already said, the fundamental concepts in the properties of signals, properties of signals, correct, properties of systems, various guiding principles, properties, and not just the properties but various principles of systems. All right, and more importantly, we are interested in this interplay between signals and systems. That is the important, not just a signal and system in isolation, but interplay between signals and systems. Specifically, correct, and you would have seen several examples of this. What happens when, let us say, I have a system, correct, I have a system which I am representing schematically over here, and if I transmit a signal x t, I have an output y t, I transmit it through a system. Now, these are the signals, x t is the input signal, y t is the output signal. So, what we would like to characterize and better understand is what is this interaction. What happens when I take a signal, transmit it through a system, look at the output signal, what is this interaction, what are the different aspects of this, how does the system act upon this signal to generate, because we are going to use systems. Systems are of fundamental importance because we have signals in electrical engineering. We would like to process these signals suitably, and for that purpose we use systems. So, we would like to understand the interplay between signals and systems, the impact systems have on signals, and also to extract a certain behavior from a signal, what kind of a system has to be designed. Alright, that is something also that we would be interesting, that is designing appropriate systems to extract certain behavior from the signals. Okay. So, this interaction between signals and systems is of fundamental importance. This interaction between signals and systems is of fundamental importance. Okay. Now, and these are used in several branches, the signals and systems, these are applied in several branches of engineering. For instance, these are applied in These are vast applications. These are applied, for instance, I have applications in electrical engineering, for instance, in the design of power systems, smart grid, you name it. I mean, there is hardly any application that you can think of. The smart grid applications in the smart grid, where you have power systems, grid of power systems, elements in the power system connected by a vast grid, and they're monitored and efficiently controlled using the smart grid. Okay. You can think of electronic systems such as TVs, radios, etc., or your mobile phones. Such as your televisions, mobile phones. You can have applications in communication systems. Communication systems such as 3G, wireless systems, or your Wi-Fi such as 802.11x systems. You can have control systems, correct, instrumentation and control, such as, for instance, in aircraft. That is a classic example of systems where there is a huge applications of control, instrumentations and control, correct, or about a plant, correct, or a factory, or where you have large installations of such control and instrumentation systems. All right. So, what this shows is basically there are a large number of systems, correct, call them electrical systems or electronic systems, etc., which use signals, which are based on signals, right, and systems to extract, right, systems to process these signals, systems to extract the desired behavior from these signals, correct. Okay. So, signals and systems is of fundamental importance in all of electrical, electronics, communication engineering. Okay. Now, so this course or this MOOC, as we have said, this aims to look at properties of both. So, the aims, as we have already said, to summarize it, the aims would be to look at the properties of both continuous as well as discrete and discrete signals plus systems. Okay. That is the fundamental aim of this course. You look at both continuous as well as discrete signals, and continuous and discrete in time, right. Look at both continuous and discrete time properties, correct, principles, right, the properties and principles of both continuous and discrete time signals and systems. Okay. Now, let us start with the definition of a signal. All right. That seems, since this course is on signals and systems, that seems to be a good place to start. So, let us start a definition of a signal. A signal can be defined as, basically it is a physical quantity, and this is of fundamental importance. All of you at some physical quantity, all of you must be at some intuitive level familiar with the definition of a signal. This is a physical quantity that conveys information about some physical phenomenon, about some phenomenon. That is the reason we are interested in signals, because a signal conveys information. For instance, such as a voltage signal, electromagnetic wave, which is a signal that is transmitted over the air from the base station to the mobile station, right? It is carrying information about the voice, it is carrying information about a communication between two individuals, let us say, or it is carrying information, let us say it is a data signal, it is carrying information about either a video or an image that has been transmitted, or the internet that is being accessed. So, a signal basically fundamentally, right, a signal, right, fundamentally carries some, is a bearer of information, all right, correct. So, a signal conveys some information about a phenomenon that we are interested in, monitoring, that we are interested in. So, it conveys some information about a phenomenon, about some phenomenon, conveys information about some phenomenon, okay. Conveys information about some phenomenon, okay, and typically it exhibits variation, because something that is constant does not carry much information. So, typically exhibits variation in either space or time. Okay. For instance, let us look at time. We can talk about a signal in time, such as an electromagnetic wave. These are all examples, electromagnetic wave, or a speech signal, a voice signal, correct. If you are looking at space, we can talk about signals in space, right, not just in time, space, such as an image, which is a 2D, two-dimensional space signal, x direction and y direction. An image is a two-dimensional signal, correct. So, an image can also be thought of a signal in space, okay. And we have signals naturally in both space and time. For instance, such as a video signal, that it varies both in space, which is a two-dimensional each frame of the video, which can be thought of as an image. So, it has variation in space as well as time, because it comprises of a sequence of frames in time. So, a video signal is very interesting in that it is a signal both in space, correct, space plus time, exhibits a variation in both space and time, that is a video signal, okay. Now, typically when we consider time signals, we represent them using x of t, okay, and these are the signals that we typically consider, okay. So, these are time varying signals, and these are typically, so for instance x of t, y of t, etc. And many principles that we develop for the analysis of such signals, which vary in time in a single dimension, can also be extended, can also be used as it is for 2D, extended to 2D, correct, 2-dimensional or 3-dimensional video signals, or a separate set of techniques can be developed for them, but based on the fundamental principles that we learn for this time signal. So, in this course, since this is a fundamental massive open MOOC course, we are going to consider the analysis of such simple signals which are varying with time, and these can be suitably extended to other scenarios, other examples which are considering, for instance, images which are 2D space signals, or video which is a 3-dimensional both space and time varying signals. Alright. So, to keep things simple, we are going to consider signals which are a function of time. Okay. So, these are signals which are a function of time. Okay. The difference between a signal and a simple function, as we have said, is its physical relevance. For us, a signal represents something, right, represents some physical quantity, correct, arising from it's some physical quantity which conveys information about some phenomenon that we are interested in. And naturally, to understand more about that phenomenon, for instance, what the other person is speaking, right, that can be a voice signal. So, understand more about that, we need to process that signal suitably. For instance, we would probably like, one of the simplest things that we would like to do is probably, since the voice is unclear because of noise, we would like to suppress the noise to make the voice clear, so that it is easier for us to understand what the voice signal is conveying, and so on. And there are a whole lot of processing right, a lot of operations that can be carried out on the signal. Okay. So, a signal, we are going to consider a time varying signals or signals which are a function of time. These are known as time signals. Now, a signal class, now let us come to a basic signal classification. Let us look at a basic classes, different types of signals. So, let us come to a classification of signals. Signals can be, well, continuous time signals, signals can be continuous time signals, such as, for instance, xt, equals sine 2 pi t, that is a continuous time signal. It is also known as a sinusoid, looks something like this, starts at 0, goes with time. So, this is x equal to sine 2 pi t. This is also known as a sinusoid or a sinusoidal signal. Either cosine 2 pi t or sine 2 pi t, both are known as sinusoids or sinusoidal signal. Or a signal, this continuous time, it's, remember, it is varying, it's defined at continuously over time. Alright, it's not defined at specific time instants, correct. So, it's defined continuously at all time instants, from either from minus infinity to infinity or over a continuous time interval. So, the point here is that the continuous time signal defined over for all instants in an interval. This defined for all time events in an interval t1 to t2, and generally speaking, if t1 equals minus infinity, t2 equals infinity, then it is defined for infinite time. But the point is, it is defined at each and every time instant, not at a specific set of time instants. Okay. So, so this is a continuous time signal. In addition, you have what are known as discrete time signals. Okay. So, these are continuous time signals. Now, we have discrete time signals, for instance, such as, which are defined at, for instance, such as x of n, correct. These are defined as, these are defined at a discrete time set of time instants. these are defined at a discrete set of time instants. For instance, you have a discrete time signal which can be defined as, this is known as, what is known as a stem plot, discrete set of time instants. Time instants can either be positive or they can also be negative. For instance, you have time 0, time 1, 2, 3, 4, -1, -2. So, these are only, it is only defined as, the point is it is only defined as, defined at defined only at a set of discrete time instants. Defined only at discrete time instants. So, it can be identified as a series or sequence of numbers. For instance, we have here x of 0, x of 1 at time instant 1, x of 2 at time instant 2, or you have x of -1, x of -2. So, these can be defined as a sequence or series of numbers. These are defined as a sequence or series of numbers. Okay. It is also known as a time series. For instance, if the signal is in time, it is a discrete time signal, a discrete time signal, all right. So, naturally, similar to discrete time signals, you can also have discrete space signals, continuous time, continuous space, discrete time, discrete space. That is, for instance, if you take an image signal and if you sample it at appropriate instance in space, points in space, this is a discrete, it's a discrete space signal. In fact, if you look at modern images which are represented as a collection of pixels, it's nothing but a discrete space signal. You have a 2D set of grid over which you have representation of the picture elements, the intensities of the picture elements, and of course, the color information. All right. So, it's a 2-dimensional discrete space signal. That's what most modern images are. All right. So, it's a time series. This is a discrete time signal, a discrete time signal is nothing but a time series. Okay. And this is a time series, it is x -1. Okay. And discrete time signals can also be obtained by sampling continuous time signal. So, I can go from a continuous time signals to a discrete time signal, and also, although it might not be extremely clear at this point, I can obtain a continuous time signal from a discrete time signal by through a suitable filtering operation. All right. But to start with, a discrete time signal can be obtained. Okay. So, I have a discrete time signals or discrete time signal. This can be obtained by suitably sampling and this is an important idea, sampling can be obtained by sampling a this can be obtained by sampling of a continuous time signal. Okay. And there are certain properties, I mean, how do we do the sampling, how can we carry out the sampling, so that information, there are a set of principles, right, and properties of the sampling process. But if you take a continuous, but broadly speaking, generally speaking, if if you take a continuous time signal, if you sample it at suitable points over a time grid, you get a at suitable points, typically points that are equispaced in time, correct. Samples, these are the samples. This is your original continuous signal. These are samples. These are your discrete signal. This is the discrete signal. This comprises the and these are the sampling time instants or the sampling instants, all right, the instants where you are sampling the signal. These are the sampling instants. So, by sampling, by suitably sampling, correct, by suitably sampling a continuous time signal, I am able to obtain a discrete signal, all right, when I want to obtain a discrete signal, okay, and we will see what are the uses of a discrete signal, what are the properties of a discrete time signal, what is the behavior, how do you process a discrete time signal, okay. For instance, these frequently discrete time signals are more convenient to process as a digital signal, correct, represent them as digital signal and process them as digital signals. For instance, in a digital communication system such as most of our mobile phones are based, for instance, most of our mobile phones which are based on digital communication systems such as for instance 3G, 4G wireless communication systems, it is convenient in them to handle digital signals which can be obtained again from discrete time signals. So, discrete time signals give rise to digital signals, correct, and these such signals are basically much more readily can be processed much more readily in comparison to the conventional systems which were analog in nature. For instance, your conventional communication systems such as your amplitude modulation radio or frequency FM radio and so on. So, for instance, examples of such systems, continuous time systems would be your conventional systems such as FM radio, TV broadcast, etc., or even conventional telephony. Your conventional telephony such as your PSTN, correct. And examples of discrete time signals would be the more modern communication systems, modern systems such as based on, of course, these are just in communication because these are easier to understand, such as your pick any modern 3G, 4G or your GSM which is a 2G communication system, or for instance all your modern communication systems such as Wi-Fi, etc., even your modern landline probably uses digital communication systems. Your set-top boxes in TV, that is a very good example for your, which are alternative to your analog cable. So, this set-top boxes for TV, that is your digital cable basically. These are your digital communication systems which represent information digitally, correct, which represent information digitally and they are processed as discrete time. It is convenient to process the signals as discrete time signals, and these discrete time signals again, as I have told you, have to be obtained by suitably sampling the continuous time signals, all right. And most of the modern systems, also I have given you examples from communication, but if you look at any system, for instance, such as based on your control and instrumentation, etc., most of the modern systems are basically digital in nature, in which it is continuous to represent and process signals as discrete time signals, all right. So, basically that concludes the basic classification of signals as both continuous, and again there are other simple examples of discrete time signals, for instance, such as an exponential kind of signal, for instance half to the power of n for n greater than or equal to 0 and 0 otherwise, represented compactly as an exponential. And if you can look at this signal, since half is basically less than 1, it is going to be a decreasing signal, something that is 1 at 0, correct. So, this is 0, 1, 2, it is a decreasing exponential, half to the power of n. Again, this is another discrete time signal, goes without saying that this is another, it is defined only at discrete time instants, therefore, it is a, this is a discrete time signal, all right. So, basically let us conclude this module with that. So, we have signals. So, this course is about the signals, the properties, correct, and principles of signal analysis and signal behavior, system analysis, system behavior, the interplay, the rich set, the rich theory which considers itself with the behavior and principles of the analysis of signals and systems and their interaction. Okay. And signals, as we have seen, are basically physical quantities that convey some information about a certain phenomenon which arise from a certain physical phenomenon, all right. And we are interested in studying the signals, behavior of these signals, modifying the properties of these signals, correct. And we begin with a characterization or classification of these signals first as two basic classes, continuous time and discrete time signals. Okay. So, we will stop here and continue with other aspects in the subsequent modules. Thank you very much.